So the valence bond theory is basically just understanding that orbitals in a molecule are not necessarily the same as orbitals in an atom. The valence bond theory also deals with atomic orbitals, which are quantum states of individual electrons in the electron cloud around a single atom. So basically talking about S, P, D, and F. So here's just a general picture of the four shapes. S is a sphere, P is a dumbbell, D is a double dumbbell, and F is a flower shape. Hybridization is where you're taking atomic orbitals and you're making hybrid orbitals by combining them, which are still localized on the individual atoms, but they just have different shapes and energies. And the really cool thing about hybrid orbitals is that they help to minimize energy, which is great because everything loves to have lower energy, which is super awesome. A couple key things to remember is that the number of atomic orbitals will always equal the number of hybrid orbitals, and that the type of hybrid orbital that occurs is the one that yields the lowest overall energy for that particular molecule, again in line with the whole energy lowering process. So let's do a quick example in case you forgot how to assign hybridization to a molecule. So the first step is to draw out the Lewis structure for the particular molecule, and we're dealing with CH4. And then the second step is to predict the electron geometry around the central atom. So around carbon there are 4 electron domains, and we can look at this super cool chart thing that tells us that 4 electron domains corresponds with an sp3 hybridization scheme. You can do this without the chart simply by just remembering that the number of atomic orbitals, aka the number of electron domains, is always going to be equal to the number of hybrid orbitals. So like we said, in CH4 there are 4 electron domains, and the 1 superscript on the S and the 3 superscript on the P in sp3 equals 4 when you add the 1 and the 3, so you are golden. A quick note about sigma bonds and pi bonds. Every bond around the central atom is considered to be a sigma bond, and then pi bonds come into account when you have double bonds or triple bonds. Sigma bonds are on the bottom in this picture, and it's when orbitals overlap completely, and pi bonds occur when orbitals overlap side by side. So kind of going through everything, this example has 3 electron domains around the carbon, so it would have an sp2 hybridization because the 1 superscript and the 2 superscript equal 3. And also talking about sigma and pi bonds, there are 3 sigma bonds, and then there is 1 pi bond, and that pi bond comes from the double bond from the sigma. The molecular orbital theory is a rigorous quantum mechanical description of bonding in which electrons are assigned to orbitals distributed over the entire molecule. And this is opposed to the valence bond theory, which we just talked about, that focuses on the atomic orbitals of one particular atom. Also, the molecular orbitals are constructed using linear combinations of atomic orbitals, because that creates a variation with the lowest energy, and lower energy is good. You can use the atomic orbitals to construct molecular orbitals. If the atomic orbitals are combined in an additive way, that creates a bonding orbital. If they're combined in a subtractive way, that creates an anti-bonding orbital. And what a bonding orbital is, that just means that the energy in the electrons is lower than if they were occupying their own atomic orbitals. And in an anti-bonding orbital, that just means that the electrons in the anti-bonding orbitals have higher energies than they did in their respective atomic orbitals, so they raise the energy of a system. This is just a picture to remind you that bonding is on the bottom and anti-bonding is on the top in the little structure, and anti-bonding is also represented with an asterisk, and the 2 atomic orbitals on the side, so the individual hydrogen atoms, they come together to make the molecular orbitals. Here's B2, and the first step in drawing these out is writing the electron configuration. So for this, it's 1s2, 2s2, and 2p1. Each boron atom in the B2 molecule completely fills S block. So each atom has 2 electrons in the atomic orbital for S. Now you have 4 electrons to work with from the atomic orbitals. So you're going to fill in the bonding first. So 2 go in the bonding orbital, and the remaining 2 go in the anti-bonding orbital on the top. A boron atom has 1 electron in p block, so when added together, it only has enough to fill the first bonding orbital, and now you're done. Just a couple more quick things. Bond order is something we have to know how to calculate, and the formula is 1/2 times the number of electrons in the bonding orbital minus the number of electrons in the anti-bonding orbitals. If it is greater than 0, that means it's more favorable for the bond to form, because that means that the number is positive, so there's more bonding than anti-bonding, and we know that bonding is energy lowering, so it's more favorable to the universe. If it's negative or 0, a bond will not form between the atoms. Just a little bit more random vocab. Paramagnetic means there's unpaired electrons, they are attracted to a magnetic field, and they're polar. Diamagnetic means there are paired electrons, they're not attracted to a magnetic field, and they're nonpolar. So back to B2, your bond order is 1 because you have 4 in your bonding, 2 in your anti-bonding. 4 minus 2 is 2, 2 times 1/2 is 1. So it is favorable to the universe, and it's also diamagnetic.